Hello and welcome to Empowered Learning. This video is the second video in the Symmetry series. And so for this particular video in particular, we are going to go through the traditional test for symmetry of a particular relation. And I'm saying relation because it can apply to a relation that is a function, well as a relation that is not a function. Examples being a circle or an ellipse. We'll also get into looking at graphs and being able to tell if a graph is symmetric about the y-axis, symmetric about the x-axis, and or symmetric about the origin. And afterwards, we'll finish up by taking some relations. Some will be functions, some will not be functions, and performing the symmetry test on them to be able to see if they are symmetric about the x-axis, y-axis, and or the origin. So let's go ahead and get started. So we see here that sometimes there may be a situation where we need to test for symmetry for a particular relation that may not necessarily be a function. And so in that, we have the symmetry test that we need to do. Now, if you watch the first video that I've done about even and odd functions, or put another way, symmetry about the y-axis and symmetry about the origin, respectively, then you'll know that there is a certain point relationship on any graph of any function that is symmetric about the y-axis or the origin. And so I'm going to start with those and then go back and talk about symmetry about the x-axis. So one of the things that we learned is that for every point xy we have on a graph, if a function is symmetric about the y-axis, then we also have a point negative xy as well. And when we were testing for symmetry about the origin, for every point xy we have, we also had a point negative x, negative y. And so this spawned us to be able to say from an algebraic standpoint that, hey, if I plug in a negative x everywhere where I see x in the function f of x, and I get negative of my original function f of x, then I know that the particular function was symmetric about the origin, or put another way, it was odd. If I came here and said plug in negative x everywhere where I see x in the original function, and I get the original function back again, then I knew that the function was symmetric about the y-axis, or what I'm calling an even function. Okay, so I'm bringing all this up because how we actually do the symmetry test traditionally are related a lot to what these particular points look like. And so I'm going to go ahead and move on to the symmetry about the x-axis and just give a simple function, well, not simple function, but a simple relation here to try to describe what's going on. Okay, so this is an example of a simple relation where we have symmetry about the x-axis here. And so particularly speaking, let's say if we know that for this, that x is going to be equal to 2. Okay, so let's say we have 2 right here. Then of course, if we have 2 right there and we want to figure out what y is, then of course what we would do is basically take the square root of both sides. Okay, and so I guess solve this for the principal root, I should say. That's a better way to say it. So in doing that, we would get plus or minus square root of 2 equals y. And so my point here is that if we come and figure out where that point is, this is messing up here. Let me try this again. I'll just erase it and start from the beginning. So let's say we have this graph here. We kind of do it like this. We know this is going to be 2. Have these 2 points there, and this is plus or minus square root of 2 for the x values there. So this point and this point are basically the points 2 comma square root of 2, and this other point here is 2 comma negative square root of 2. So that's what I was trying to draw there. So in looking at that, we see that for every x value, we have 2 corresponding y values. Now we know that's not a function, but we also see that this particular graph here, this relation is symmetric about the x-axis, okay? And mainly that's because we see that we have a reflection or a mirror image of the function that's on top here, down here on bottom below the x-axis there, okay? And so this is why we say that for every point x, y we have on the graph, we also have a point x negative y as well. And so why all this is important is because when we do our symmetry test, what we need to know is what we need to replace in the particular relation to be able to test for that particular symmetry, okay? And so I'm going to scroll down here so that we can kind of see what those steps are. Now, whenever we have symmetry about the x-axis, notice that we want to replace everywhere where we see y with a negative y. Well, the reason for that is because we see that for a given x value, if a particular relation is symmetric about the x-axis, it's going to have a corresponding y and a negative y. So that's why when we do this algebraically, everywhere where we see y, or if I put f of x, we would want to replace this with a negative y, or put another way, a negative f of x. Similarly, if we do symmetry about the y-axis, now you see that the x values are the ones that change. So this is why everywhere where we see x, we want to replace it with a negative x, okay? And for origin, we see that both x and y change. So that's why here we want to be able to take everywhere where we see x and replace it with negative x. Everywhere where we see y, replace it with a negative y. And so our goal here is to simply do the replacement that we say based upon what symmetry we're trying to test, and see if we get the original function back again, or original relation back again. If we get it back again, then we know that it is symmetric about that particular axis. If we don't get the original relation back again, then we know that it is not symmetric about the that particular axis, okay? And so in essence, that's what the steps 2 and 3 say here. So after step 1, solve for y, and then if y equals the same thing you started with, then it is symmetric about the x-axis. And of course, that kind of repeats here and here as well, okay? One of the things that we do know is that any type of relation that is symmetric about the x-axis cannot be a function, okay? So one of the reasons why we even test for even and odd in that first video is because whenever we're dealing with functions, we know automatically that it cannot be symmetric about the x-axis. So that's why we don't even try to test that, because it wouldn't make sense to do so, okay? But for this particular lesson, because we're trying to, I guess, look at more things than just functions, we want to get into the traditional symmetry test. All right, so we're going to quickly look at these graphs right quick and be able to tell if these are symmetric about the x-axis, y-axis, origin, and from that, we'll be able to just judge, okay? Okay, so let's go ahead and determine for the following graphs whether they are symmetric about the x-axis, y-axis, or the origin. So for our first graph, if you notice, we see that it's sort of a wave type shape. And so to be able to test to see whether it's going to be symmetric about the x-axis, y-axis, or the origin, or neither, we can take a couple of points. So here, let's take this point and this point, and let's see how they're related. So if we look at this, we see that we have 2 pi here. So of course, right in between would be pi. So this would be pi over 2 for the x value. So that would be negative pi over 2. And of course, for here, this value should be a negative 1. This value should be a 1. So we have a point here that is negative pi over 2, 1. And we also have a point right here that is pi over 2, negative 1. And if you notice, both the x and y coordinates are opposites of one another. Okay. Now, similarly, if we look at this point here and this corresponding point on the other side, which is this, we see that this is going to be, if this is pi right here, then this is going to be 1.5 pi, or 3 over 2 pi, with a 1. And this point here is a negative 3 over 2 pi, with a negative 1. And if you notice, both here and here, the x coordinates are opposite of each other, y coordinates are opposite of each other. So from what it looks like this particular graph is going to be what we call symmetric about the origin, meaning that it's an odd function. So we know that. From the points, we don't see the situation happening where it's symmetric about the y-axis, meaning that we have 2 corresponding x values for every one y value. We didn't see that happen. And we didn't see that we have 2 corresponding y values for every x value. So we'll say that graph A is just going to be symmetric about the origin. If we look at graph B, we see clearly here, just kind of by common sense, that this particular graph will be symmetric about the y-axis here, because it kind of folds across. Okay, so we're going to say this is symmetric about the y-axis. Of course, since we have nothing down here, it wouldn't be symmetric about the x-axis, so that would be out. And of course, for the origin, for every point, let's say we had right here, we would actually have to have a corresponding one, let's say down here somewhere, and we don't have that. So we know that this is not going to be symmetric about the origin either. So for graph B, this one will just be symmetric about the y-axis. For graph C, this one also looks like another one that will be symmetric about the origin, only because this looks a lot like the function 1 over x. And so if we plugged in a negative x everywhere where we saw x, then of course this ends up being the opposite of the original function. Okay, so if this is f of x, that's negative of f of x. So this appears to be odd. We'll check out some points just to be sure. So for this one, an easy point to pick would be this point right here, which that would be the point 1, 5. And another easy point would be this one right here, which would be 5, 1. Now, if we have a point 1, 5 and we expect this to be symmetric about the origin, then we are suspecting to have a point negative 1, 5. Negative 1, negative 5. Here, let me do that again. We're suspecting to have a point negative 1, negative 5, as well as a point negative 5, negative 1. Okay. Now, if we look here, we see that whenever we have x is negative 1, if we look here, we are, right at this point right there. Let me erase that other one. So that would be this point right here. So that is the point -1, -5. And then if we have, we're also looking for the point -5, -1. So when x is -5, which is right here, we look up, we see that we have this point right here, which is at y equals -1. So we do have that correspondence there. So because of that, we could say that this particular graph is symmetric about the origin. Okay. Now, since the graph doesn't go like this, then of course it wouldn't be symmetric about the x-axis. And because the graph doesn't go like this, it wouldn't be symmetric about the y-axis. All right, so let's move on to our last two graphs here. And so for D, we see that this is another one that kind of looks like it's symmetric about the origin. Okay. Now, if it was symmetric about the y-axis, we would have a part that goes like that, but of course we don't see that. And of course, if it was symmetric about the x-axis, then we would have a part that kind of goes like this, at least for this part, okay? But we don't see that. So for this one, we will just say that it's symmetric about the origin. We'll erase that then. For this last one, if you notice, for this point here, we have a reflection about it on the x-axis. And let's say for this point here is a corresponding reflection about the y-axis. And then of course, if I had, let's say, a point right here, then I have a corresponding point there. So for this one, this is actually symmetric about the origin, symmetric about the y-axis, and symmetric about the x-axis. Okay? And so for most circles and ellipses, we do have that case where that particular graph ends up being symmetric about both x and y axes and the origin. Okay? So to sum it up, we know that the ones that have symmetry about the x-axis, we see that we had only one, which was E. Symmetry about the y-axis, we had B and E. And symmetry about the origin, we had A, C, and D. A, C, and D. And of course, the ones that involve no symmetry, we didn't have any that involved that, so we're okay when it comes to that. All right, so moving on here, next thing that we want to do is actually see some examples on how to test for symmetry. So if you remember, if we test for symmetry about the x-axis, then we know that the one thing that is in common is the x-coordinate, so that means the y-coordinate would change. So this is why we would take y and replace it with negative y. If we were testing for symmetry about the y-axis, then of course we know that the y value is the thing that stays the same, so now we will replace x here with negative x. And of course for the origin, you have to change both x to being minus x and y to be minus y to test that. And so in either case, our objective here is once we do that replacement or substitution, then what we want to do is solve for y to see if we get our original function back again. And of course, for this first one here, we see that our original function was just y equals 2x squared minus 3. And so once we have negative y here, we can multiply both sides by -1 in order to get y by itself. And we see that we get the negative of 2x minus 3, which is not what we need. So we know that it's not symmetric about the x-axis. About the y-axis, we see that if we replace x with negative x, and here's what we started off with, here's what we ended up with. And it looks like the exact same thing. So because of that, we know that this particular function here is going to be symmetric about the y-axis. And then of course for the origin, you can see when we work it out that same deal here, we end up with negative y right there, multiply both sides by -1 to see if we can get the original function back again. And unfortunately we got the negative of the original function back again. So we know that it is not symmetric about the origin. Okay. Now, please do not get this confused with the even and odd test. When you do the even and odd test, what you are trying to find out is if you replace negative x everywhere where you see x, do you get the original function back, which is even, or do you get the negative of the original function back, which is odd? Whenever we do the traditional test, what we're actually doing in that case is doing the replacements and seeing if we get the original function back every time. Okay, and we're doing it for all three of them. So that's the main difference here. For the traditional symmetry test, we're trying to find, do we get y equals the same thing every single time? Okay. All right, so let's go ahead and look at some examples of our own here. So we're going to test for symmetry about the x-axis, y-axis, and the origin, just so that you see how it works. So symmetry about the x-axis, I'm going to name this y, and everywhere where I see y, I'm going to replace it with negative y. Okay, and so now if I multiply both sides of this equation by -1, then what I'm going to get when I do that is going to be -6x cubed minus 2 equals y. And of course, what we have here does not equal what we originally started with, which was 6x squared minus 2. So we know that it's not symmetric about the x-axis. Okay. Now let's do symmetry about the y-axis. Okay. So here we know that the y stay the same, so we're going to replace x with negative x. So in this case, we are substituting or evaluating the function at negative x. And so this will end up being a negative 6x cubed plus 2. And again, we're comparing to see if what we have right here is the same thing that we originally ended up with. And so that is not true there either. So there's no symmetry about the y-axis. So last thing that we'll do is say symmetry about the origin. So in this case, we have to replace y with negative y as well as x with negative x. And so when we do this, we know that the negative x quantity cubed is just going to give us a negative x cubed, which makes this term a negative 6x cubed plus 2. And then from this point, we can multiply both sides by a -1. And so from there, we distribute. So that would be a 6x cubed minus 2. And then that would be a positive y. And so if we look there, we see that this particular one does not equal 6x cubed plus 2 either. So at the end of the day, regardless of what we have, we know that this particular function in this case is not symmetric about the x-axis, y-axis, neither the x-axis, y-axis, nor the origin. Okay, and of course that makes sense because one of the things that we know is that this particular function kind of looks like this. So it doesn't go through the origin anyway, so there's no way for it to be symmetric about the origin or the y-axis or the x-axis. Okay. All right, let's move on to our next example. So for example B here, we see that this is not a function, and the reason that we know it's not a function because our y is squared. So for every x value that you have two corresponding y values that could go with it. And so we know that that's not representative of a function. But we will do the same test here. So we'll start off with symmetry about the x-axis again. And so in this case, since we know that the x values will stay the same when we have symmetry about the x-axis, we need to change the y. So everywhere where we see y, we put a negative y. And then of course, negative y squared is just negative y times negative y. A negative times a negative is a positive, and y times y is y squared. And so we see that this is the exact same thing that we ended up with, so that we started with, I should say. So this checks out, and this is symmetric about the x-axis. Okay, so we're going to check just for formality, is it symmetric about the y-axis and the origin? We're thinking that it should be no, but we're just going to see anyway. So now that we're testing for symmetry about the y-axis, everywhere where we see x now, since the y is going to be the same, we replace with negative x. Okay, and so now what we do is solve for x in this case, because that's what we originally had. And we can do that by multiplying by a -1. And you notice sometimes I put just a negative here, and other times I put explicitly a -1. Doesn't matter what you do as long as you understand that you need to multiply by a negative and change the signs. So when we have that, we end up with this. And of course, that is not equal to y squared minus 1. So of course, symmetry about the y-axis is no. If we do symmetry about the origin now, then of course we're changing both the x and the y. So just like how we've done before, negative y quantity squared is this, and we multiply both sides by a -1 again, and we see that this is x minus y squared plus 1, and of course that's not equal to y squared minus 1. So here the only symmetry we have is about the x-axis. All right, moving on to our next example. For this one, we are suspecting that this is going to be even because all of our terms have even exponents on it. Okay, so to prove that, we will actually go and go through the test here. So I'm just going to stay consistent, do symmetry about the x-axis first. So here, for symmetry about the x-axis, we replace y with negative y. And then of course, we multiply by -1. Kind of got the drill at this point. Everything just changes sign. And of course, this does not equal to what we originally started with. So we have no symmetry about the x-axis. If we do symmetry about the y-axis, then of course we're changing everywhere where we see x to a negative x. And of course, a negative x quantity squared is just a positive x squared. which leaves us with 2x squared in the first term. And then, of course, here we have to remember we cannot do the negative times a negative as a positive here, or subtract a negative number as addition. We can't do that yet because we have this exponent here. We need to respect order of operations and actually do the negative x raised to the fourth power first. And in doing that, we know that negative x raised to the fourth power is just negative x times negative x times negative x times negative x. And since we have an even number of negatives, we know that we're going to end up with a positive answer for just this portion right here. Just that, not including the subtraction sign there. So in seeing that, we know that negative x quantity to the fourth is just going to be that. And now, if we look here, that's the same exact thing as what we started with. So just as we were thinking, we saw that this was symmetric about the y-axis. And so just for show, we'll show that this is not symmetric about the origin by both changing the y's and the x's. So here that ends up being 2x squared minus a positive 4x. And then, of course, we multiply both sides by a -1, which changes the terms. And, of course, that is not equal to 2x squared minus x to the fourth. So no symmetry about the origin. All right, and so for our last example, we'll do the same thing here. So we have symmetry about the x-axis. So again, for symmetry about the x-axis, since x is going to stay the same, we change everywhere where we see y with a negative y. Of course, we'll just multiply y by -1, which changes all the signs for each term. And of course, this is not the same as what we originally had. Okay. So no symmetry about the x-axis. Okay, and of course this makes sense because if we had symmetry about the x-axis, this would not be a function, and we know that it is a function, so that shouldn't have worked anyway. If we do symmetry about the y-axis, then y stays the same, so now we have to plug in negative x everywhere where we see x. Okay, and so now in doing this, we get 4x squared plus x plus 3. And again, this is not equal to what we originally started off with. So we have no symmetry about the y-axis. So the last thing is symmetry about the origin. So we change everywhere where we see y, we have negative y. Everywhere where we see x, we have negative x. So here we know negative x quantity squared is just positive x squared. Subtract a negative is the same thing as addition. And so now, of course, the negative y here, if we multiply both sides by a -1, it changes all the signs in each term. And of course, we see that this is not equal to what we started with. So this is another one where we end up not having symmetry about neither the x-axis, y-axis, nor the origin. Okay? So this concludes the series of videos on symmetry and testing for symmetry given a relation or a function.